Okay, so welcome to today's EE Colloquium seminar. Today I'm very happy and privileged and honored to introduce Shwetak Patel, who's our own faculty here in both EE and computer science. I am very glad that I brought an iPad today to introduce him because it's appropriate for his research, and also because I wouldn't be, if I were to have printed out his bio, I would have wasted a lot of paper because it's so long and impressive. So, Dr. Patel, he's a professor here. He got his PhD at Georgia Tech. And he's been doing a number of very, very interesting and actually quite amazing things, as I'm sure you'll hear in his talk. He's primarily working on ubiquitous computing and sensor-enabled embedded systems and user interface technology. He founded Zenzi Incorporated, which is an energy sensing and feedback company, which is actually very interesting and actually will hopefully save us all ultimately lots of money. He received a number of impressive awards, including the TR35 award in 2009. He was named Top Innovator of the Year by Seattle Business Magazine in 2010, was named Newsmaker of the Year by Seattle Business Journal in 2010, was named the most influential person in Seattle Magazine in 2011, received a Microsoft Research Faculty Fellowship in 2011, and Sloan Fellowship Foundation, it's quite a few, in 2012. And also was given a MacArthur Genius Award. And I hear that he's about to win the Nobel Prize. So, so congratulations. Let me be the first to congratulate you. Very good. So I will now turn over to Shwetak. Thank you very much.
Thanks, Joe. It was interesting. I think my wife was able to predict the MacArthur Award. It was we're getting back on some flight from Washington, D.C., and she was like, and we got some press for some of our research, and it was interesting. She was like, oh, they need to give you one of these MacArthur things. And obviously, we have no clue who gets nominated, and she had no idea. But 3 days later, I get the phone call, so she's apparently a psychic as well. So I want to spend a little bit of time today to talk to you a little bit about our research that we're doing in my lab. And so our research actually focuses on a couple of different areas: ubiquitous computing, which is the idea of bringing computing technology outside the desktop metaphor into the real world. Human-computer interaction, looking at ways that we can build applications on top of computing technology, new sensing systems and embedded systems to support them, and user interface technologies. Another way to kind of look at the work that I do in my lab is in these four rough areas. One area that we work a lot on is on sustainability sensing, so looking at new sensing technologies for monitoring electricity, water, and gas consumption in the home. Health sensing, so new sensing technologies to support a variety of different health applications. New user interaction technologies, again, like I mentioned, moving away from the desktop and mouse metaphor, what would it mean to be able to interact with a computing technology that's in the environment, in the physical world. And also new low-power wireless sensing technologies. And so what I want to do today is give you a sense of the various different projects that we've been working on in my lab. And so I want to talk a little bit about the sensing work that we've done for the home environment, in particular our energy and water monitoring technology, some of the low-power wireless sensing work that we're doing, and some new user interface technologies that we're building. And then at the end, I want to hint at some of the new health sensing projects that we're working on as well. And so the focus of this talk is to kind of give you an overview of these different areas. So the goal is to mainly give you an idea of all the stuff we're working on rather than trying to go in depth into one area. Part of the reason for that is in the next couple of months, you'll see my graduate students doing a dissertation, defenses, generalist exams that are much deeper in these areas, and I'll let them do all the hard work. And also, they're much smarter than me, so I'll let them do that as well. But I just want to give you an overview of the kind of things we've been working on. But also the message of this talk is actually two things. One is kind of the title, which is the noise, your noise is my signal. So one of the things that you'll notice in the themes of the work that we do is that we come up with really interesting ways to take noise and use it as our signal and in very unusual ways. And so that's one of the things I want to kind of highlight in some of the projects that we're doing. The other thing is I want to tie this talk together in a very different way. Typically, you try to cluster it based on what projects you're working on, the depth of a particular research area. Here, I want to tie it together in a different way, which is how we ran into problems in one project led to a solution in a different project. So the idea here is that when you get stuck on a problem, instead of just giving up on it, what we said was, let's take that problem and make it a solution to another problem that we found. All right? And so that's one of the things I want to highlight is as I move from project to project, you'll see how a problem in one project ended up being a great solution for another project. So it's an interesting way to think about how you string research projects together. So let me first talk about some of our energy monitoring work. So often when people approach me, they're like, well, why do you focus on the residential space? Isn't it the giant tower that's down the road that's consuming all this energy and water? And that's sort of true. It turns out that a significant amount of our energy consumption, both gas and electricity, about a quarter of it is actually what we do in our daily lives, in our homes. And so that's actually a significant portion. And it's a portion that we can actually have an influence on. These are the things that we do in our day-to-day activities. In water, it's actually even more interesting that more than half of our water consumption in the US is actually residential water use. So this is potable, treated water. So this doesn't include irrigation water that's reclamated and that kind of stuff for farms. This is basically treated potable water that needs to be pumped, all right? And so that's more than half of our water consumption is what we do in our daily lives. And so there's really a need for looking at the residential side of the problem because that's a really tough area to actually move into just because of the diversity of homes and how people live their lives. And so if you think about what kind of feedback do we have in the energy space right now in our homes is, the analogy I like to try to talk about is a grocery shopping experience. So let's say you're grocery shopping, and at the end of this experience is you get this nice itemized receipt which tells you exactly how much you bought and where you spent your money, and you get a nice total at the end. And Safeway, for example, starts to cluster your receipt to tell you, how much are you spending on groceries, refrigerated goods, baked goods, which is kind of a cool way to figure out, well, where are you spending your money? But what if I told you that Safeway wants to do something really different and say that they just want to tell you how many food units you purchase, in this case 1,527, and how much you owe, right? I mean, you probably wouldn't like that because you want to know where you spent your money. You want to see if they charged you incorrectly or whatnot. But it turns out this is precisely how you're actually billed for electricity and water. So at the end of the month or every 2 months, what you get is two pieces of information: how much energy you've consumed or water have you consumed, and how much you owe at the end of that month. Other than that, you don't get any information at all. We've been used to this for the last 60 years. So if I were to give you a credit card bill or a telephone bill that didn't give you a breakdown, there'd be a huge backlash, right? But in the energy space, we've been used to this. So this makes no sense. Because it turns out that a lot of the environmental psychology research has showed that if you give somebody a breakdown of their energy bill, you can actually see a 15 to 20% reduction, sustained reduction in energy consumption just based on people's behavior changes. That's using the humans as controllers in the system without having to have any additional control systems in the whole problem. But the problem is, how do we enable an itemized electric and water bill? It hasn't really, we haven't ever seen that. And there's technology already in your home, right? There's this thing called a meter, but it's pretty ugly, it's esoteric, the units make no sense, kilowatt hour, CCF, what does that really mean? That's not really actionable in terms of what you could do to save energy. So this is usually only used for billing purposes only. And so if you try to think about how you can build this, this itemized electric or water bill, well, one model might be to distribute a bunch of sensors throughout your home. So you can actually, install a little power meter behind your microwave, your coffee maker, your bean grinder, and then your refrigerator, but then all of the other lights in the house. I mean, this is just the kitchen and only a small subset of the kitchen. So obviously, a sensing technology that uses a distributed technique won't scale. And so one of the things that we've been looking at is, well, how do we make the sensing technology so simple that it's a single or one or two sensors in the home that gives you a breakdown of your energy use? And so one of the techniques we've been using is actually using the utility, the electricity, the water utility, as a sensor itself. So the analogy here is if you use a network, so if you have an Ethernet cable, and if you were to splice into the Ethernet cable, we can actually snoop network activity to figure out high-level activities. Similarly here, we can actually snoop on the utility infrastructure to figure out energy use in a different way. And so the tap point is actually a single sensor. And so one project we've been working on is called ElectriSense, which is a single sensor that plugs into any ordinary electrical outlet. So you don't need one for every appliance. It's just a single sensor for the entire home that basically looks at the power line noise to infer what kind of devices are being used on that power line. And so, the existing approach is, this is not a new approach in terms of trying to break down your energy use. This goes back into the 70s. But in the 70s, what they started to do was they looked at power. They looked at the power readings on your meter to say, well, if you see a 1,000-watt load come on, that's probably a toaster. If you see a 10,000-watt load, it might be a dryer. But it turns out these days that doesn't quite work because there are a lot of things in your homes that are 100 watts. All right? And so it's hard to tease that apart if you only look at the power consumption. In fact, if you have a lot of things turning on simultaneously, you can't separate a lot of those events. And so what we've been looking at is not just look at the current that's coming into the home, but we actually look at the voltage. In other words, we actually look at the noise that emanates over the power line based on the use of these electronic devices. And there's two things that is interesting about this. One is you can sample anywhere in the home. You don't actually have to be behind the particular appliance. You could be parallel to an appliance. And and it gives you this additional set of information that the power information doesn't give you. So, what generates a lot of this noise signatures? It turns out that, as we become more and more efficient with electronic devices, we're seeing these switch mode power supplies emerge. Instead of having a linear regulator, you have a switch mode power supply because it's more efficient. We're in a mode where more and more devices are actually switch mode power based. And so what the side effect is, it has an internal oscillator that actually leaks EMI back over the power line, and it produces continuous EMI noise over the power line. And so if you think about what kind of devices have switch mode power supplies, actually lots of devices. In fact, more and more are being mandated to have these things, all the way from your CFL lighting to your television, entertainment equipment, the chargers and the power adapters and your computing technology that you have in your home. So for example, if you look at a spectrogram on the power line, so the x-axis is the frequency domain and the y-axis is time, so basically a waterfall plot. It turns out that you can actually see the center frequency of the oscillators that are all of them that are in your home on the spectrogram of your house. So this is just an example of what the spectrogram looks like up to 133 kilohertz. And you can see where the CFL resides. You can see where the television is. These are all basically the internal oscillators and the power supply design that's being leaked over the power line. And so this is a really interesting piece of information. Even if you have multiple things on simultaneously, because they occupy different parts of the spectrum, you can start to tease that apart. And so using current and the EMI noise, we can start to break down the energy use now. So how do we do this? So I won't go into too much detail here, but I'll just give you the high-level ideas behind this. First, we actually model the different kinds of loads you might find in the house using a circuit model. So a CFL has a very different load characteristic versus a television. So in this example here, a CFL has a burst signal. So basically, when you heat up the gases in the tube, you actually have a burst, and then it basically calms down to whatever its center frequency is for the oscillator. And so that actually is very indicative of all CFLs. So we're using the circuit model to reverse engineer what the EMI will look like, and then from the EMI, we can figure out the circuit model. That gives us a good guess at whether or not it's a CFL or a television or a laptop. So if you look at a different load, let's say we zoomed into here on the TV is even more interesting. So the TV's power supply is modulated based on the backlight. So as you're watching a movie or a show, the center frequency of that power supply is switching to keep up with the load characteristics of the TV itself. So if you have a bright scene, it'll move right. If you have a light scene, it'll move left. And so a CFL is not going to look like that because it doesn't need to dynamically change its power characteristics, whereas a television does. A PC or a laptop has yet a different characteristic. And so that's what we've been doing is from the EMI noise, we reverse engineer the circuit model and guess at what kind of device it is. And so incidentally, I won't talk about this in this presentation, we've actually been able to use the EMI noise on the power line to infer what you're watching on TV. Because that signature tells you what the scene transitions are. And so what we were able to do was mine the Netflix database to figure out what the EMI noise would be. And based on a little sample, a 5-minute sample of the EMI noise in somebody's home, we can actually figure out what they're watching. Pattern match it to a movie, for example. So that gives you an idea of how rich this data is on the power line. So how do we sense this? So the sensor is actually pretty simple. It's basically a physical connection to the power line. I mean, it looks like a little box that plugs into an outlet. So there's a a high-pass filter, which has a corner frequency of 36.7 kilohertz. The key here is you've got to knock out all the 60 hertz. So because we're looking at the high-frequency noise, anywhere from 50 kilohertz to up to a megahertz. The filter that we use goes up to 30 megahertz. Then our digitizer, or DSP, basically samples at about a megahertz. So we're only looking at about up to 500 kilohertz right now, because that's where a lot of the switch mode power supplies operate. But more and more of them are starting to operate at a higher frequency, so we're going to boost that up a little bit. And then all those features are basically sent to the classifier for modeling what these different devices look like and then inferring what it is. So there's two processes we have here. One is a trading process that you can do where you can label different devices by turning them on and off. But the other method that we've actually started to employ now is actually doing this in an unsupervised way, where we actually have models of what these devices look like, and then we can start to guess at this without even training the system. So that only gives us event information. So when a TV turned on and off, when your laptop turned on and off, how do we get power? All right? So there's two ways to get power. One is we can actually telemeter this data from a smart meter, but we're assuming that a smart meter doesn't exist, and we can't even get that data. So how do we get power consumption information? Traditionally, the way you'd have to do this, you'd actually have to put CTs inside your breaker panel, and it requires an electrician. The average consumer can't install this, because the goal for the work that we're doing is easy to install. And so this definitely doesn't scale because it requires an electrician. Even an electrical engineer can't do this. I can do it because I'm incidentally a certified electrician. But you'd have to get inside your breaker panel. So what we built was actually a device called the stick-on power meter, or a contactless current sensor. So So this little sensor actually literally tapes onto the outside of the breaker panel. And so what it is an array of magnetic sensors that picks up the magnetic field induced by the bus bars behind the breaker panel door to infer what current you're consuming. And so the idea behind this is you can actually start to get power consumption information without having to go inside your breaker panel. So it's a really hard problem because of the metal in between it. You get a lot of nonlinearity effects. But the idea behind this is we're actually constantly calibrating the sensor. Remember that device that plugs into the wall that's monitoring the noise also pulls a known load every now and then throughout the day, which telemeters data to this sensor, and it calibrates it. So over the course of a day, it'll pull a 5-watt load, then a 10-watt load, and then quickly do a 1K load. And then over time, you can actually create that function, that transfer function. And so now you can actually build a really easy to deploy current sensor. So with these two sensors, we can get power information and event detection that's still easy to install. And so it turns out this is actually pretty accurate. We're within 4% of an actual power meter. So we did a number of evaluations. This slide is a little old, but for 7 homes, we actually painstakingly instrumented the home with ground truth sensors to see how well this technique works. Over 100 devices. Think of how many electronic devices you have in a home. And these are, you have hundreds of them per home. And so, so the average classification accuracy with a false positive rate of less than 1%. So very few of these, we're actually very good at finding the events, and a lot of them are actual electronic events that are happening in the home. Is for a nearly 100 class problem, it's about low 90%, so 92%. So what this means is if you turn on a television with 90% accuracy, we know that it's that television that turned on, right? So something that's interesting is some of these homes here on the right, home 5 and 6, it's a little bit lower, which is, home 5 and 6 is because the kind of loads that they have in the home was interesting. They had a lot of lighting in their house. And so it's really hard to tease apart from the different lighting from the different room. So if we were to cluster all the lighting as to one category, then obviously the accuracy would go up. So we were being very aggressive here. This was a per appliance level classification. So it's the lighting in the bedroom versus the lighting in the living room we were trying to disaggregate. So this was probably one of the harder problems that we were trying to solve. So what can we do with this? So here's an example user interface that we've built. This is basically an iPad interface that I actually use in my house. So it gives you how much you owe, how much you've consumed, how much you're consuming right now, and how much you've consumed for the last 7 days. So you can see how well you're doing compared to the last few days. And so the idea here is that you can get a breakdown of your energy use. So the breakdown also in percentage of how much that is being contributed to your bill. So 19% is my main floor lighting, refrigerator is 10%, and this indicates if something's on or off. So I usually take a quick look at my phone or my iPad to make sure that things are off. So this is kind of a dashboard you might find in a house. So this was an interesting picture we took. We're doing a front cover page on a book where they took all the appliances out of a house where we installed the technology to basically show what devices consume how much energy. So a lot of times when people see the data through our deployments, it's actually pretty surprising. Pool pumps are kind of obvious. They consume a lot of energy. For this particular home, 31% of their energy consumption was a pool pump, but 11% was actually the DVR. They had no clue. The DVR is something out of sight, out of mind, right? You don't see it. It's not like the lighting that you use all the time. It's just always running in the background. But it turned out for this particular home, that was a top consumer. That was like number 2 or number 3 on the list. Because it's a 50-watt load, they have 4 of them running all the time. In fact, the DVR consumes more energy than all their kitchen appliances put together in the course of a month, right? So a lot of these things are eye-opening because you don't really have a lot of visibility into where you're consuming energy. And so that's why disaggregated energy consumption in an easy-to-understand way is important. So here's another report another interface that we built, which basically shows you a breakdown. So you can see at the high-level categories how much energy you're consuming, and then it breaks it down to the different lighting. If you want to say which room is consuming how much energy versus which television, it gives you that breakdown as well. Here's something that's really interesting. So I started a company many years ago called Zensi, which was acquired by Belkin. And so now a lot of the technology is actually being used commercially, which is great. It's really exciting for the students to see the impact of the work. But this is actually an energy bill that ComEd gives their customers, which is based on our technology. So you don't just get a bill now. You actually get a breakdown of the big consumers. So for this particular home, it's the electric water heater, then the air conditioner. And it tells them not only if they're doing better next month, but how they compare to their neighbors for that same kind of device. So you really get a lot of feedback in terms of how well you're doing and how you're compared to others. And now a number of these homes are actually getting breakdowns like this on their energy bill. And so this is an actual bill from one of these homes that's getting this kind of information. And obviously, they can log in and get a deeper breakdown, just like what I showed you on the iPad interface. So that's the ElectriSense project. So we ran into a problem with ElectriSense, which leads me into our next project. So one of the problems we ran into with ElectriSense was when we were looking at some of the CFL data, it turned out that when people kind of came close to a CFL, the signature changed for some reason. So we had to account for that in our model. So we're like, what? So when you have a lot of people in a living room, why is the CFL signature changing? And so on the right here is the signal actually changes in frequency and some harmonics appear. And so we tried to solve that problem, and we came up with a model to get around it. But we actually took that and looked a little bit closer, and we created we actually worked on another project called Lightwave, which is we actually figured out how you can use ordinary CFLs and fluorescent lighting in a building as motion detectors without having to instrument the CFL itself. So the idea behind this is actually you can use the CFL as a sensor for human motion detection, and you only have to sense all the information from one location, which is this ElectriSense hardware. And so the idea behind this was that if you look at a CFL, you have the thing that the light you basically have the gas-filled lamp. And so when this thing is lit up, it ionizes that tube there, and that basically ends up being an equipotential electrode. And so the field that's generated around that can actually be modified as a person approaches it. So you can actually detune the internal oscillator as a person approaches the CFL. And so what that means is, as people approach the CFL or moving underneath the CFL, that EMI noise actually changes based on how people are moving around. Basically, what's happening is you're detuning the oscillator. And so what we can do with this is you can turn any CFL with very little modification into a motion detector-based lighting system. Because what people have been doing now is they actually have a separate motion sensor in their lighting, have a relay in it, which turns on and off the lighting as people are going in and out of a building. But the problem with that is it requires a lot more hardware, it's more expensive. But here we can actually use the CFL itself as a sensor, which with a few pennies, you can make this into a motion-detected lighting system, where it can actually turn on in a really dim mode, so you can actually see something, and then when people walk in, it actually turns on. And so this is something that we've been doing with a project called Lightwave. Other thing that's really interesting is we're able to do gestures. So if you're under a lamp, let's say you have ceiling lighting in your house, you can actually gesture with your hands, and we can detect how many fingers you're holding up based on the detuning of the internal oscillator. So you can actually do in-air kind of gestures under your lighting, which is kind of interesting. But the whole idea behind this was that the sensor itself you can use as a motion detector. So that was something that was an interesting side project we did as a result of some problem we ran into with ElectriSense. So there's another problem we ran into also. So when we were looking at these spectrograms, there are a lot of EMI noise sources that we couldn't explain where they came from. For example, that thing on the right, what is that blip every second? We had no clue. We couldn't figure it out. We turned everything off in the house. We couldn't figure out what it was. It turned out that we were actually seeing AM radio stations on the power line. The power line is a giant receiving antenna. So what can we do with that? So that's what led to our low-power wireless sensing project, which was using the entire copper in a building or a home as a large receiving antenna for wireless sensor networks. So that's what this motivation was for this project. The idea behind this is, the idea behind sensor networks is you can have sensor networks. Sensors are going to be distributed throughout the whole environment. One of the things that we're really good at is we're really good at wireless communication. We've kind of figured that out. But the challenge right now is that they're hard to maintain, right? Why? Because of the giant battery packs that you'd have to kind of replace all the time. If you had 1,000 sensors in the home environment, it's not going to scale because of all the batteries you'd have to replace. So getting the power down to a point where it's manageable is a real big concern right now. And so what we did was we actually worked on a new project called Snoopy, Sensor Nodes Utilizing Powerline Infrastructure. So this is with Gabe, Cohen, Jagdish, and Brian. And the idea behind this was to build an ultra-low power wireless sensor node that would scale in any home or any building environment and would try to address this power problem. So let me just show you the data first. So you've probably heard of sensor networks all the time. Yet another sensor network. So why is the UWEE Comp Lab working yet on another sensor network? So if we just look at the power consumption of the transmit, so if we take all the existing sensor nodes that are commercially available, set them up in the same way as our sensor node, so 10 kilobits per second output, fixed transmit output, all right? So one of the things to first notice is on traditional sensor nodes is the TX, or the transmission, the communication portion dominates the power consumption over the microcontroller, the computation inside of it. Whereas Snoopy, it's the opposite. Our TX is actually orders of magnitude lower than the microcontroller inside of it. So there's this interesting reversal and communication transmission a power relationship. The other thing is that our transmitter actually is 2 orders of magnitude to get the same range as the existing nodes. Right? So 2 orders of magnitude. And the overall power consumption is 1 order of magnitude lower. All right? And so the question is, well, how is that possible? All right? So it turns out there's 2 things we're doing. So on the right, we've actually have optimized hardware to do this. But actually the key component here is we're utilizing the power line infrastructure in a new way. The idea is, like I alluded to earlier, is that there's only one receiver in the building or the home, and it's plugged into the wall. So instead of having an antenna, we actually use the power line as a large antenna. And that's what allows us to dramatically reduce the power consumption of our transmitter. All right? And so the power line actually acts as a large receiving antenna. And so here's an illustration. So here's how traditional wireless works, right? You have this base station with bunny ear antenna sticking up. If you have a node in the bottom left corner of your house, you have to actually turn up the power enough so you can get to that base station, right? But in the Snoopy approach, we use Powerline coupling. So there's no antenna there because the antenna is the power line. So if you had that same node, you only need to transmit close enough to get to the antenna. All right? So you can turn the power down. Even if you're in the middle of a large room, you don't still need to go over the air to the other side. Or to get to you only need to get to the closest wall. And so that's what we're doing here, is we're actually using the power line as a way to extend the antenna. In fact, an interesting anecdote is that as a home gets bigger and as you get more walls, traditional wireless, you actually suffer in performance. Here, it gets better. As you get more walls and as the home gets bigger, it works better, which is an interesting change in a mental model as well. So this is strongly frequency dependent. You can't just put your Wi-Fi router into the power line and hope that it works. It turns out we did a pretty thorough analysis of the different frequency of the spectral frequencies to see what works well. It turns out the way that the geometry of the Romex cabling of the electrical in a building or a home is actually resonant at about 27 megahertz, 27 to 45 megahertz, and luckily 27 megahertz is the ISM band. All right? So this is a really low frequency technique, but it works really well because the power line is a perfect antenna on the receiver side, which means we could be sloppy with the transmitting antenna. So our transmitting antenna is on this sensor node, which is just a few centimeters on the side. So this is the Snoopy node. It's fully programmable, long battery life, so it runs on a low coin cell battery. It's low throughput. Right now it's 10 kilobits per second. But the transmitter on this only consumes 60 microwatts, and you get whole home or whole building range. So it has MSP430. In fact, the MSP430 is the lowest power microcontroller out there, but it is our bottleneck right now because that consumes significantly more power. So we're going to work on a custom chip with Brian to figure out how we can get this thing down even lower power. So here's some range tests, which are kind of interesting. So we took a home where we installed the base station arbitrarily on the lower floor. So that triangle there is where the base station is plugged into the wall, and the blue dots indicate where the tests were made. And so what we did was we basically got the signal-to-noise ratio. So pretty much we got pretty good signal everywhere. Above 15 dB, well above 15 dB, almost 30 to 40 dB in a lot of locations. And note the transmitter was set at 65 microwatts. So there was no automatic gain. It was fixed at 65 microwatts. And we're still getting whole home range. And this is a fairly large house. This is about a 3,000 square foot house. End to end, we're getting data. But it was interesting to see that our hypothesis about being close to power lines held, because a lot of places where you were close to power line, it worked well. But in the middle of the rooms, it kind of the performance went down, so we'd have to turn the power up a little bit. And corners of rooms where you might not have an electrical outlet, you might not have wiring, obviously there was lower signal. But another thing that was kind of fascinating was we took a lamp and moved it to the other side of the room. It increased the performance by 30 dB. Right? It's kind of interesting to move a lamp, right? And the idea is because the extension cord is also part of the antenna, all right? So it really changed the game about how you would extend the range, right? Often you try to look for a sweet spot. Here you just move a lamp and it increases your performance. So it's a fascinating problem. But like I said, the power lines can be extended with extension cords. The plumbing is also interesting. Those 2 circles there is actually the bathtub. These weren't jacuzzis. These were normal bathtubs, didn't have any power. But we put the sensor node in the middle of the bathtub. It's because this house has copper plumbing. So the copper in the home from the plumbing also acts as an extension to the antenna as well. So what can we do with this? So the idea behind this work is long-lived sensor deployments. So because it's so low power, we can actually run off of a coin cell battery for over 20 years, depending on the kind of sensor you have on it. So now you can actually imagine hermetically sealed sensors that you throw in an attic, crawl space, and not even have to worry about replacing the batteries. In 5, 10 years, you just throw another sensor set down there. And so that's what we're doing right now. We actually spun out another company called WatchFrog that's commercializing Snoopy to basically enable sensor deployments at a mass scale in homes where you could do lead, humidity, mold detection without you even having to worry about going into the attic or crawl spaces. And so the idea here is that with low throughput, low power sensors, you can actually start to enable that vision. All right, so next project. So we ran into problems with both ElectriSense and Snoopy. So what problems did we run into with those projects? It turned out that not only is the EMI that's propagating over the power line conducted over the power line, it's also radiated off the power line. So when you see a CFL turn on, you don't just see it when it's conducted over the power line. The power line also radiates that energy back off of it, which caused massive problems with our receiver node because we were seeing data being coupled to the sensor itself because it's being radiated. And we also found that when you touch the Snoopy node, it changes the receive characteristics of the node itself because the body actually is a pretty interesting antenna as well. There's also been a lot of work in body area networks where if you put a sensor node on one side of the body and you have another one on the other side, you want to use the body to communicate. But the fact that things are always radiating from the environment causes problems with body area networks. So what we did was we actually used that as a solution to another problem, which was creating new user interface technologies. So the idea behind this is, can we build a sensing gesture system that uses the human body as a receiving antenna based on all the EMI noise that's being radiated out of the environment? So the idea behind this was, can we build a Microsoft Kinect without having the Kinect in the room? So the idea is you don't have a camera facing you, but you use the changes in the complex geometry of the human body as a way to infer what gestures people are performing. And so that's what we did in collaboration with Microsoft Research. So with a single ADC on the body, so you can have this in a pocket or on a wrist or whatever, you can actually use the body as a receiving antenna, use the body antenna effect to detect what people's gestures are. Because as you move your body in different poses, you're changing the frequency response of your body's antenna. All right? Actually, I'll just show you a video of this. I think that's just the coolest part of this one. Is that, so we basically try to emulate what you could do with the Kinect with the various different gestures. And so this is going to show the various different poses that we can detect in real time. And so these are just, so this is a 12 class problem. So he has 12 gestures that are basically modeled in the system. And so here, there's no Kinect. There's no camera in front of him. The only thing that he has is the sensor node that's on him. All right? And this is using the body effect. And the signal source is anything. It's basically the power lines, the 60 hertz, the EMI that's being generated from that TV in front of him. We don't have a signal injector. It's all passively detecting this from the environment. And so the interesting things are you can start to do these really interesting gestures. But more interesting is that you don't have to worry about the traditional camera problems like occlusion. You can actually have somebody in front of him and multiple people interacting with this, and it doesn't cause a problem. You can have people on the side, for example, and still it works because it scales to anywhere in the environment. In fact, he could be in the kitchen doing these gestures, and it still works. So he did the canonical Tetris game, so rotating a piece and then sidestepping to move the piece left and right. I don't think this is how I would play Tetris, but anyway, let me go down. So here's the cool part. So he's going to actually do a kick, punch, punch, and he's going to turn around and do the same gesture, and it can still detect it. And whereas a camera-based technique might not be able to pick it up because you're occluding it with your back. All right. Okay. So that's one project that we basically, and this is a project that we're working on with Microsoft Research that's actually gotten a lot of attention lately. And so this was kind of an accidental finding. All right. Then yet there was another problem. So with the human antenna project, which I just showed you, there was something that we saw in the data, which was this kind of interesting constant DC offset. And we couldn't explain where we're seeing this DC offset. We understood the 60 hertz, we understood the EMI, but there was this constant DC offset we saw in the body signal. And we're like, what the heck is that? So we started digging. All right. Again, we modeled it out, we canceled it out, but then we started to dig a little bit to figure out what was it. it actually led to another project that we did with Josh and the folks at Josh Smith here, and also the folks at MSR, which was using the human body for static E-field sensing. So the idea behind this was, so what we found was basically we were detecting the static E-field in the environment. So this device was a sensor that's on the body, and we're basically we're actually observing the E-field that's in the environment passively. So traditional capacitive sensing technologies for user interfaces typically have a time-varying electric field that you induce, and then you see how that changes, all right? But what we actually observed that actually it's everywhere. So you don't actually need to make a signal. The E-field is always existent. And so what we were able to do was we can actually use this technique to build an on-body accelerometer. So when you move different parts of the body, you can actually use that to detect motion at different parts of the body. Okay? But the cool thing about this is that typical accelerometers consume, 400 to 1,000 microwatts. If you find a really great one, it's 100 microwatts. This technique only requires 3 microwatts. So you can actually do on-body motion detection, like what an accelerometer does, with 3 microwatts of power. So you can use this to wake up an accelerometer if you want high-fidelity data, or just use the signal directly as an accelerometer. All right? So the idea here is that the body is actually coupling to the earth ground, and we're actually picking that up as you're moving different parts of the body. Again, this is much better explained with a video, so let me show you that. All right, so this is a sensor node. So this is a little watch that you wear. All right, so here's the trace. So the top is actually this data coming back from our sensor. And the bottom 3 traces are accelerometers. So we put an accelerometer on that wristwatch to show you what it looks like when you compare the accelerometer to our E-field data. So the top is E-field stuff. It's not an accelerometer. So as he moves his body around, see how well this tracks with this, right? So he can do the normal stuff. So he's explaining the stuff. So that's a sensor. So as he moves his body, he can actually, the top is actually the E-field. It's basically accelerometer. It tracks really well to the accelerometer data here, which is the Z-axis, right? So this is normal stuff, right? I mean, this is maybe not that exciting because you might as well put an accelerometer there. But watch this. He's going to hold his left arm steady and move his right leg. All the accelerometers are completely quiet, but the E-field sensor still picks it up. So in other words, by sensing one location on the body, you can detect movement anywhere on the body. So if you if you're walking, you can do gait detection. You could do arm movement detection, so jumping. So obviously that'll pick it up. And so here is, instead of having accelerometers all over the body, you can actually use the static E-field sensing technique to basically emulate multiple accelerometers, but from one location. So yeah, so he's holding his left arm completely steady, and then gesturing with his right arm, and you can still see that, right? And again, and the power consumption for this technique is only 3 microwatts. So he's demonstrating a variety of different techniques here, where what we were able to do is we actually took accelerometer data and our E-field data, and we built a classifier to detect walking, running, jumping, sitting. And in fact, we could actually, with the same level of accuracy with the E-field sensor, detect those events, which is really interesting. In fact, we could detect events that were happening elsewhere on the body with that sensor hand held completely steady as well. So this is a brand new project that literally we just worked on just a few months ago. All right, so that's all the electricity sensing work. So I'm going to switch gears a little bit to water sensing and talk a little bit about that. So similar to how we worked on ElectriSense, which was disaggregating or breaking down energy use down to each appliance, we actually have a project called HydroSense, which looks at building, again, a single sensor that's end-user installable that can break down your water consumption down to each fixture. And so this is a number of different students, Eric and John working on this in collaboration with James Fogarty and Les Atlas here in EE. So the problem with water is even more challenging, because where do you install the sensor? I mean, here you'd actually have to cut into a pipe. And you don't want the average consumer cutting into the pipe because, I mean, it's not a really easy thing to repair. So the idea here is we have to come up with a really easy way of installing this that doesn't require pipe modification. And so inline water metering doesn't quite work well because you have to cut into a pipe. So what we've actually done is we've used a different technique. So if you look at what the plumbing layout is in a home, you typically have water coming in from the street, and then it basically is a branch network. All right? Hot and cold is actually tied together. A lot of people think hot and cold are separate. They're not, actually. There's a giant capacitor there, which is called a water heater. All right? And that's going to make sense in a little bit. So what our sensor does is we actually install it anywhere on the plumbing line at the periphery. So in this example, the sensor is literally just screwed onto a hose bib because we're not measuring flow, we're actually measuring water pressure changes. So we're using pressure fluctuations that emanate throughout the entire plumbing infrastructure to infer water events. So this could actually be at the hose bib, it could actually be at this little drain on the water heater, or you could put it anywhere, under a sink or a toilet or whatever. Typically, it's easy to put it on a hose bib because you can just screw it on. All right? So from that one location, we can monitor hot and cold water activity, because if you have something that's generated on the hot water line, it actually couples through the hot water heater. And so what are we detecting? So what we're detecting is when you flush a toilet or open and close a water valve, you have something called water hammer that is created. So water hammer is basically the resonances that are created from the valve activity. So what this is a dramatic change in water pressure that's occurring. And so sometimes water hammer can be heard acoustically. So sometimes when you flush a toilet, you might actually hear the pipes banging in your house. That's actually a more gross version of that, right? But if you actually look at the pressure data, you can actually see that even if you don't hear the acoustic resonances. So this is what some of these signatures look like. So the top is a faucet, the middle is a toilet, and the right is the bottom is a tub. So what's interesting is, depending on the valving of the kind of fixture, it's a different signature. So an electromechanical valve in a dishwasher or a laundry machine is going to be different from a manual operated hand valve, right, which is a ball valve, versus a toilet, which has a flapper valve in it. And so the valving actually dictates the kind of fixture it is. So that's one thing we can do, is we can model the valving based on the resonant frequencies that are generated. So we can tell if it's a toilet or a tub or a faucet. All right? But the other thing that's really fascinating is we can actually tell apart different toilets from each other, even though the shape is the same. What's different is the characteristics of that waveform. So you can think of the piping infrastructure as a transfer function. So if you have a toilet upstairs and downstairs, even though the shape is the same, the dampening effect is actually different depending on where the toilet resides relative to the sensor. So we can actually start to say that you have 2 or 3 toilets in your house, not just that a toilet consumed water. On the left is an example of the sensor screwed onto a hose bib. So literally, it screws onto a hose bib, and it's Wi-Fi, and it communicates to the router in the house, and all the algorithms just run in the cloud. So this is what a bathroom sink looks like. This is actually not simulated data. This is actual real data. This actually looks this clean. So this is when it's first flushed, or sorry, the bathroom sink is open, and then when it's closed. So you can see the resonances that are generated from the valve activity. And the pressure drop is what we use to infer flow, right? And so what we do is we actually have 3 different signatures. One is a fixture type signature, which I said, based on the valving technology that's being used, we can try to infer what kind of valve it is. And then the valve location is dictated based on the different characteristics of the home plumbing network. So that requires a training process, obviously. But in terms of identify the category of those events, we've actually created a global model to do that. So the algorithm has 4 steps. First, we detect when a water event happens, which is basically just a drop in pressure. And that's actually a really great event detector. So we first detect if it's an open or close event. That's really easy to do by looking at the derivative. If it goes up or if it goes down, that tells you if it's a close or open event. And then we try to classify what it is, if it's a toilet or a sink or a shower. And then based on that pressure drop and our pipe model, we can actually start to inflow how much water is going to that particular fixture. So this was a painstakingly hard data collection process. So one of the things that you probably realize in our lab is you got to go into the real world and collect lots of data. So we actually built these sensor boards that were attached to every water fixture in all our deployments to get ground truth information. So if you had a single handle valve or 2 handle valve, there was a sensor on every valve in your house. In my house, it looked like a rat's nest of electrical wiring, and a lot of other poor souls as well. But this is how we had to get ground truth data. And so in our first evaluation, where we did a 5-week deployment, we had about 15,000 water events. And so what we want to do is try to evaluate the accuracy of our system. So when you had isolated events, which was you turn on the water fixture, you turn it off, it's pretty easy. It's almost nearly 100% accuracy. But the hard ones are when you have compound events, because when you flush your toilet, you better wash your hands. And so that compound event is when you flush the toilet, water is filling in the toilet, and then you're washing your hands. That's actually a compound event. That actually makes things harder because you have things that are superimposed on top of each other, and superposition doesn't always hold. All right? And so there, the accuracy obviously drops a little bit. It goes down to 90%. But still, pretty good for more than 2 events. But it turned out in our data that most households actually don't have more than 2 or 3 events at the same time. Because if you think about it, if you're trying to take 3 showers simultaneously, what happens? Well, first of all, the water pressure drops dramatically. Secondly, the hot water runs out. So it turned out just logistically, you don't see more than 2 or 3 events at the same time. When you do, it's only 20% of the time. So even though our accuracy for compound events is only 90%, we only see compound events 20% of the time. But luckily, a lot of the confusion was among similar fixtures. We misclassified the upstairs toilet versus the downstairs toilet. So again, at a category level, we can boost a lot of the accuracy here. The other things we're doing beyond some of this work is looking at how we can do leak detection and infer when the flapper in the toilet valve, for example, is still running. So there's other things we can do to offer some value there. So here's an example of what the water interface looks like. So it's very similar to the electricity interface, where you get a breakdown of your water consumption and then how much you owe thus far, how much water you're consuming. So if you run your water faucet, you can see how much it's consuming in GPM. Again, a comparison for the last 7 days to see how well you're doing. And at the bottom here is a breakdown based on the different fixtures in your house in terms of gallons. So this can really be a conversation piece to help you figure out where water is being consumed. All right, so that was the HydroSense technology. And I want to briefly talk about a new project we're working on in the health sensing space. So again, here it's a really different signal, right? So in the past couple projects, we were using EMI generated over the power line, pressure noise on the water infrastructure. Here we're actually using a different side effect. So this project is called SpiroSmart, which was the idea was to build a mobile phone-based spirometer. So what a spirometer is, it's a device that individuals with chronic asthma, COPD, or cystic fibrosis use to measure lung function. So it's basically integrating how much air you can expel through a 1 second or 6 second period. Basically, it measures lung volume over a course of a certain amount of time. And so they use this this is a mainstay for diagnosing chronic asthma, COPD, and a lot of other conditions. In fact, they look at these spirometry charts to figure out if they want to change the albuterol levels, for example. But the way this is done is you have a tube that you blow into, and it has a turbine in it that basically measures how much air you're actually pushing through. But the problem with this is a home spirometer is fairly expensive and bulky to carry around. And compliance is actually very low right now. So what we want to do was build a mobile phone application that could do spirometry. So the idea is you would actually hold the phone arm's length away and you blow at the phone. And can we get the same kind of information that we would from a spirometer? All right? And again, using only the microphone and no additional hardware, because we had to make sure that this thing could scale. And so that's what we've been working on recently. But the problem here is that, unlike a traditional spirometer, which uses a turbine or a pneumatic or an ultrasonic approach to figure out airflow, we could only rely on the microphone. And so what we do is, because we don't have a turbine there, because again, the requirement is no additional hardware, we actually use the lip reverberations and the vocal track as a way to infer flow. So typically, the way people have been doing flow assessment using the microphone is you look at the velocity across the microphone itself. Well, we actually look at this other side effect, which is when they're blowing as hard as they can at the phone, we're actually looking at the resonance that's generated by the vocal tract and the lips to use that as a flow sensor. And from that, we actually created a model that tracks pretty well to actual spirometer. And so we actually did a study, the slide's not in here. We did a study with 52 patients where we basically took the charts that were generated, the patient charts, the doctor charts that were generated with a traditional spirometer and replaced them with SpiroSmart results. And we didn't tell them that. And so we wanted them to see if they made the same diagnosis with a spirometer. And it turned out on a 5-point scale, which is non-obstructive to all the way to obstructive flow, they were able to very accurately, even as if it were a regular spirometer, identify what level of condition they had. And so we were getting the same measures that the spirometer was getting. And so the way this works is with the 52 participants, we actually created a global model. So this isn't trained per individual. But if you train the system at a doctor's office, for example, with a clinical spirometer, you can obviously increase the performance. But it turns out of the box, this works pretty well. So we're actually scaling this up to a large clinical trial and getting FDA approval for SpiroSmart, because this actually really changes the way that you can actually start to do pulmonary care. Right? So the analogy here is that you have diabetes monitoring solutions at home, you have blood glucose monitoring technology in the home, you have blood pressure technology in the home. You actually don't have good spirometers in the home. So this is a way to really scale this pretty quickly. All right. So that's kind of what I wanted to talk about. There's a lot of stuff I couldn't talk about. We only have an hour. If you're interested, go to the lab webpage. We have a lot more information about this stuff. Some of the things I couldn't talk about was we're actually using some of our energy monitoring technology for health and elder care applications. It turns out because we're getting so much rich information about human activity, we can actually use that for some elder care applications. So for example, there's a group that's taking our work and basically using our water sensor data to see if you can use water patterns, changes in water patterns throughout the day to infer the onset of a congestive heart failure or changes in somebody's diabetic condition. Because it turns out toileting habits changing over a certain period of time is an indicator for a lot of these physiological phenomena. And so by using the water data, it's an unobtrusive way of getting at that information. Like I kind of alluded to this before, but we're looking at a lot of different privacy implications with the leaked EMI. So we really have to think about how we can secure a lot of this data because we're creating an interesting data set about people's activity. We have to be really careful about what we can glean from that information. We've also done a number of other projects, including human antenna on gesture-based interfaces. So one is Soundwave, which is using the microphone and speaker on a laptop to do in-air gestures. So this is something that we've been getting a lot of press about recently. Another thing we've been working on using thermal imaging for user interfaces. So the Microsoft Kinect has a depth camera and an RGB camera. What would happen if you added another dimension to it, which is thermal imaging or a temperature at every pixel? So we've looked at combining depth sensing RGB cameras and thermal cameras to do really robust gesture recognition. And a number of haptic feedback projects on the bottom, ranging everywhere from emulating a spring in software to self-powered haptic feedback systems, even remote at a distance haptic feedback systems. So what that means is, imagine you're using the Microsoft Kinect to play a game. What would it mean to actually, as you move your hand to hit a ball, you actually feel the ball, but you're not wearing anything? All right, how can you remotely or at a distance send enough energy to actually have force feedback on a hand without you having to wear anything? So that's kind of a sneak peek at what we'll be doing this year. All right. So in summary, I just wanted to kind of point out the various different projects we're working on, mainly around how you can look at signals that are kind of in unusual places and really using them to solve interesting problems. And with that, I'll take questions. Thank you.
Questions? So I have a number of questions actually. So a number of times you said that you use a classifier. And I was wondering what kind of classifiers are you actually using?
Oh yeah, that's a great question. It totally depends on the technology. So for ElectriSense, for example, which is identifying the electrical appliances that are being turned on and off, that's actually a SVM-based approach. So most of our techniques actually support vector machines. So most of them are SVMs.
Okay.
Yeah.
So, a question?
You're talking about the Snoopy as a replacement to the Wi-Fi in a big house, right?
Okay.
So how is this, is this, so your transmitter is basically transmitting at 10 kbps, which is not close to the Wi-Fi standard. So how do you envision this happening?
Yeah, so the question is, how is this a replacement to Wi-Fi? So the question is, it's not a replacement to Wi-Fi. It's a separate sensor network, right? So what I was saying was, using Wi-Fi as an analogy, right? For Wi-Fi, it's over the air. Here, what we're doing is we're using the Powerline as a receiving antenna for the Snoopy sensor network. So it's not a replacement for Wi-Fi. So the idea here is for sensor nets that are low throughput sensor networks that require very low power consumption. So we're working on ways to actually get that up to 1 megabit per second, for example, but that's still far out. But yeah, no, it's not by no means it's a Wi-Fi replacement. In fact, Wi-Fi won't work because the power line is not tuned to 2.4 gigahertz. Yeah.
How do you tell two electrical appliances apart, like if you have two laptops?
Yeah, that's a great question. So let's say you have two Samsung televisions, same brand, same make, same model, right? So their internal oscillator will be maybe at 150 kilohertz. And so if you look at the spectrogram, interestingly, they're not on top of each other. So the internal tolerances of the electronic components is about 5 to 10%, right? So because of those tolerances, if you zoom in, because the resolution that we can resolve the FFT bins is pretty small. So what that means is when you zoom in, you actually see two traces that are next to each other, not on top of each other. So we see the television turn on and off, right? But if two of them are on at the same time, we can, from the way that they operate, we can say that's a television, but they're actually separated by a few FFT bins. So we leverage the fact that the imprecise nature of a lot of these oscillators is that they have a 5 to 10% variance in them already. So eventually, if you have 20 Dell monitors, they're going to collide eventually. Yeah.
When you do all this kind of training data for some specific house, if I put all different kind of consumer electronics or appliances there, and I collect some training data, I do SVM training. But after those training, if I use those SVM to the other different house, what am I going to do?
No, so you can actually do that. So we've actually been creating a training set in the cloud that basically has a database of these signatures. There's many different ways to get the signatures, right? I mean, we've even hired people to go to Best Buy at 5 a.m. in the morning to turn on and off different electronic devices and get the signatures. That's one way, right? Another way is we can actually use people using the system. So for example, let's say Xbox comes out with a new Xbox 760 or whatever, or 720 or whatever. And so what will happen is on the interface, it won't say Xbox 720. Right? What will happen is it will say gaming console. But somebody at some point will modify that and say, no, that's not just a gaming console. That's my new Xbox. When they label it, it actually helps everybody else. So that label gets sent to a database, and it populates everybody else's training model too. So we apply the examples from one house to the other because they do transfer over.
But normally for electricity usage in one room because of the wire pipe, their signature might be different in different rooms.
Yeah, the power line, I mean, the impedance on the power line, the line inductance, I mean, it causes because that transfer function is going to be different home to home. But what we do is we're picking out the high-level features that is independent of the power line infrastructure, and there's still enough of that there. Yeah, that's a good question. That's one of the hardest things that we've been solving right now is how do you take the home-specific transfer function, pull it out of the waveform that is more generalizable. Yeah.
Okay, other questions? Okay, well, let's thank you very much.